Okay, good morning. So we'll start this new topic, thin film deposition. Okay, so this is a very important process. In fact, you can see in material science department and so on, they actually have complete course on thin film deposition. Now, if you look at the VLSI or semiconductor processing, I think I mentioned this to you. There are basically two types of processes. One is additive. Okay, so you take a substrate, you add stuff onto it, right? And then the other is subtractive. So you remove the things selectively, because when you do the addition, usually or in many cases it is not possible to add things onto a substrate at only places where you want them. So we'll see that, and then so you need to remove these materials from places where you don't want. So thin film deposition is a very important additive process where you are adding things onto the wafer now or substrate, and you can see there are many deposition techniques, and we would cover only a few of them, and these are relevant for VLSI applications or most of the silicon semiconductors. Now you can also see that there are several processes like spray coating and so on and so forth, which we would not discuss, even though now these kind of processes are actually becoming increasingly important because we have a very low cost process. So I have right now 3 PhD students who are working on spray coating of extremely thin films, and this is a process you use for spraying the painting your car, right? And so it is very cheap. You can just do it in atmospheric pressure, in clean room ambience, and we are also now discovering or actually realizing that you can really make extremely thin films like 10 nanometers and so on are very much possible. Yeah. So in the past, people thought that it can be like few hundreds of nanometers, right? But now you can scale it to very thin films. So, we would not look into those kind of processes, but even though they are very interesting, important for many applications. So this is an outline. So you can see the introduction, physical vapor deposition. So if you look at the thin film deposition processes used in VLSI, you can classify them into two processes, like physical vapor deposition and chemical vapor deposition. Okay, and in the physical vapor deposition, we will cover these things. What is conceptual system? Evaporation is a very important and commonly used technique. Film growth, how does it happen? Sputter deposition, pulse laser deposition. And I should mention that most of the VLSI applications, you use sputter deposition, but these are important because many of the PhD students who work in the clean rooms to make devices actually use a lot of this evaporation, and some of you may actually use pulse laser deposition processes. And then there are this chemical vapor deposition process. Now, if you look at this, just to come back, so we do have in the CN labs all these deposition tools. Okay. Then you have the chemical vapor deposition. So you have the thermal CVD, so which we will use for looking at the CVD kinetics, plasma enhanced CVD processes, and then so these are very common, right? Thermal CVD and plasma enhanced CVD processes. And you can see the classification of CVD can be based on various things like how do you supply the energy required for the process to work. So you have thermal, which means you're heating up the substrate, right? Plasma is where you actually crack the chemicals precursors by using a plasma. Okay, and within plasma itself, you have several varieties depending on how you create the plasma. Okay, and then hot wire CVD. So here you actually break the precursors using a hot wire. Usually the wire is made of tungsten, so you can actually heat it to very high temperature. Then light induced CVD, so you use optical energy, electron beam, so electron beam energy, and so on and so forth. So if you look at these processes, we have, I think, here everything except the light induced CVD process available in the labs here. And then atomic layer deposition is a very important process that was kind of invented in 1960s by a Russian scientist, but then it languished for a long time, but now it's actually becoming very, very important. So we'll see this process as well. Yeah. So in fact, in the VLSI industry now, for gate stack deposition, people use atomic layer deposition tool, and we have again in the lab this ALD tool. And in fact, one of the colleagues from energy science and engineering, he actually makes this ALD tools. Okay, none of these tools are very complicated. Of course, if you want to take them to production, where the uniformity, throughput, and so on are very important, then it becomes a big challenge. Now, if you look at this physical wafer deposition, yeah, so what is involved? In both these cases, physical and chemical vapor deposition, one common thread is the vapor. Okay. Now, in physical vapor deposition, you have a source which is at least one of them would be a solid, yeah, and which is evaporated or sputtered. So you are actually heating this, right? Evaporation means, you know what is evaporation, right? So you heat it, and then vapors of this material would come out. Or sputtered. So what do you mean by sputtering? So you have this material, you bombard this with high energy ions, okay, like argon. Yeah. So then, let's say I want to sputter aluminum. So I bombard the surface of an aluminum sheet with argon ions, and argon would not react with anything, right? It's an inert gas. So you would get aluminum particles coming out of this surface if the energy of the argon ions are sufficiently high. And then it gets transported through some medium, okay, usually vacuum, and the material would then condense on the substrate to deposit the film. Yeah. So very simple process, right? And now if you look at the examples I mentioned about thermal evaporation, so this is not a VLSI process, but it's used for making a lot of semiconductor devices, small volume production, laboratory experiments, and so on. E-beam evaporation is a cousin of the thermal evaporation process. We'll see why. They are very closely actually related. Pulse laser deposition, similar. In all these cases, you are evaporating, yeah, things by heating. Now, how do you heat it? Is the distinction between them. Now, physical sputtering is another process, right? So you are bombarding a material with high energy ions, and then you can use them in different conditions. For example, molecular beam epitaxy is a very important process, okay, and we will see why this is an important process later on. And we do have actually in the lab now, I think 2 or 3 molecular beam epitaxy systems. Okay. Chemical vapor deposition, you have a source which is fluid. So this would be either gases or liquids, or you can also start with solids, but then they should be converted into a fluid form. Okay. What gets delivered though into the reaction chamber would be a vapor or a gas. Now you have a chemical reaction between the sources on the surface, Yeah, this is very important. Okay. In the physical vapor deposition, what you are doing is the material you want to deposit is what is actually being evaporated or sputtered. Okay. And it can happen that this stuff actually reacts with something on the way, during the transport. But here, the chemical reaction that results in the final film formation actually happens on the surface of the substrate. Now, I mentioned about this different processes, and you can classify these into various categories, based on the source of energy, right? So you have a thermal CVD, hot wire CVD, plasma enhanced CVD, photon assisted CVD, E-beam assisted CVD, ion beam assisted CVD, and so on and so forth. Okay. So depending on how do you provide the energy for the process. And then you can classify this based on the pressure at which you actually conduct this reaction. So you have atmospheric pressure CVD, APCVD, right? And then there is a LPCVD, so low pressure CVD, high pressure CVD, okay? So you go to very high pressure, and then you have the ALD, very close cousin of CVD process, so atomic layer deposition. Now you can have a thermal ALD, you can have a plasma enhanced ALD, and so on. Okay. Now we will see these things. I would not be discussing much about the high pressure CVD, but I would mention briefly that this is a very interesting process for making artificial diamond. Now, if you look at what is the importance of this thin film deposition in VLSI, so we can, what I have done here is I took one of the old processes we used to actually use at IMEC to make, let's say, 90 nanometer node transistors. Yeah, so long time ago I left that place in 2006. So up to we are actually looking at a process where you make the transistor, okay, and you deposit one level of metal. Okay. So as I mentioned, and we have seen before, that a VLSI chip can have 9, 10, 12 levels of metallization. Okay. We are looking at the process till the first metal is deposited. Okay. So it uses, in this particular case, 4 sputtering steps. So all of them were metals. Okay. Nickel, titanium, and so on and so forth. CVD, 15 processes. Okay. Thermal is like used for depositing crystalline silicon, silicon nitride, silicon dioxide, polysilicon, titanium nitride, and so on. PCVD, plasma enhanced CVD processes, 10 steps. So silicon nitride, silicon oxide, phosphosilicate glass, PSG stands for phosphosilicate glass. Silicon carbide, black diamond, this is again some form of carbon. Okay. This is a trade name for a process that applied materials has developed. And then you have dielectrics. So if you look at what type of materials are deposited by these processes, most of them are dielectrics, semiconductors, 2 metals. Now, if you look at the importance in materials research, so this is actually a very important thing, because when you want to study a material for a certain application, okay, which process would you prefer to use? Yeah, you are actually exploring a new application for some material. Okay, so you have the choice PVD, so physical vapor deposition processes, and the other is CVD, right? And now also ALD. So a lot of considerations. What it requires is you need a target, okay, for sputtering or charges for evaporation. So essentially pieces of the material, okay. this would be actually a plate. Okay, so you need a larger dimension, typically larger than the substrate on which you are depositing. Okay. Now, it's very easy to get high purity charges. For example, if I want to deposit aluminum, yeah, I can actually buy 2 kilograms of 99.999% aluminum for maybe 50,000 rupees. So, high purity charges are easy to get. I can machine them. So, we got, for example, for an applied materials tool here, got this huge block of aluminum, got it machined in Thane, yeah, nearby, and used it in the tool. So, you can actually get them and handle them very easily. For example, gold. So, the lab uses a lot of gold. Okay. And this is bought from ICICI Bank in Hiranandani. Okay. So, you can get them. Some of them are expensive, like platinum, right, can be quite expensive. But so as a consequence, if you have high purity targets, you can actually deposit very high purity films. CVD, on the other hand, has a problem. So, you need the reactants typically in gaseous, liquid or solid form, but these are not the final materials you want to deposit. So, they would go through some chemical reactions. Okay. So, that is why you call it a chemical vapor deposition process. Now, the precursor should have sufficiently high vapor pressure. So, if I start with a solid, I need to actually convert it into a vapor form, okay, a liquid, the same thing, right, and they should have sufficiently high vapor pressure. So, typically in the range of 1 millibar at room temperature, okay. So, this is kind of, it's a thumb rule, but you can see people then try to do, if I start with a solid source, right, and then you try to convert it into some vapor by chemical reaction or by heating and so on and so forth. And now the challenge starts, the precursor should be sufficiently pure, okay. So, if I take the deposition of aluminum, okay, one of the precursors that is used for CVD processes is trimethyl aluminum, yeah. So, trimethyl aluminum, what is the chemical formula? AlCH3, 3, yeah. So, you have aluminum bonded to 3 CH3 groups. Okay. Now, this is, what is the problem with this? No problem, except that this is highly inflammable, okay. So, I need to worry about, so this would spontaneously catch fire if it comes to contact with moisture and oxygen, okay. So, this is very dangerous, yeah, it will catch fire. So, you need a very sophisticated arrangement to actually handle this material, okay. No leaks can be tolerated if I am going to use this, and it should be sufficiently pure, okay. So, I am talking about a very difficult to handle material, but it should be purified to like 5969 and so on and so forth, purity levels. So, anything that is there in a precursor can actually contaminate your film, okay. So, even if let us say the trimethyl aluminum is extremely pure, the film that you deposit can still contain hydrogen, okay, and carbon. In a PVD, sputter deposition process or evaporation of aluminum, okay, you may just, you start with aluminum, you end with aluminum. Yeah? So, you can get extremely pure materials. So, this is one problem, and also means that if you want to look at new materials, you should synthesize precursors which have these properties. So if you, I actually, when I joined here, we wanted to do something on ALD and MOCVD deposition of some high K dielectrics and metals, and we do have actually colleagues in chemistry who actually synthesize the precursors used for those depositions. Okay, but the problem is that I approached one of the colleagues and said that I'm interested in this kind of materials. Can we work together? He said that this is going to be for research. Yeah, if I take somebody to do this, and it's a 2 year for synthesizing at microgram level. Okay, and then beyond that he is not interested, because that's when you get a lot of publications for a chemist, right? But after that, microgram to milligram to grams is not going to give you any publication. But of course, that would be the next step, would be maybe 3 years more. So this is not an easy task. Now, there are many precursors which are poisonous, as I already mentioned, inflammable, corrosive, and so on and so forth. Handling them can be quite a challenge. Now, if you look at the properties that are interesting and important, both physical and chemical are very important. Okay. Why are they? Actually, as electrical engineers, we are interested in their electrical and maybe optical properties, not necessarily the chemical properties. But obviously, the electrical and optical properties would be dependent on the chemical composition and the thickness and what type of contaminants are there actually in the film density and porosity, okay, refractive index and optical absorption, defect density. So typically it refers to particle in contrast to contaminants, okay, and step coverage. So we'll see what is step coverage shortly. Please switch off your mobile phones. Okay, step coverage. So if you look at this step coverage, this itself suggests something to do with a step. So how it covers a step. So that is what it means. But we have to quantify. So what is seen here is actually a trench, clearer here. So you have a trench etched into a substrate. So this is silicon, dark region is silicon, and you have etched a trench into it, and then a film is deposited. Okay, so the film is deposited at the top, covers the side walls, bottom, and then goes up like. Now this is the same film deposited at 350 degrees centigrade. Okay, what difference do you see? What do you see? So the thickness on the sides is not the same as the top. Here, these two thicknesses are closer. Okay, so this is what is referring to step coverage. So we'll formally define it. Now, what is the problem? Suppose I want to run a conductor, a piece of metal line through such undulation. Okay, which one would I prefer? I want to just connect two transistors on the chip, and the metal has to run through some uneven topography, right? So which one would I prefer? That one, because this would actually result in a higher series resistance, right? A thinner film, higher resistance. What are the other problems? What about something called electromigration? Electromigration. Okay. So electromigration is something we'll discuss very shortly. But you can, maybe I'll discuss it right here. So if I have something like this, okay, or let's say I take this example, right? So you have current flowing through this metal, supposing that this is a metal, okay, it's not necessarily a metal in this particular case. So current flows through this like this, right? And the chip may be running at high temperature, okay, and a high current flows through this metal. So let's say I have aluminum and the chip locally is running at 150 degrees centigrade, okay, and this would be a very thin film. So this is a micrometer, right? This dimension. So this may be about 200 nanometers, 150 nanometers. Okay, extremely thin film. So I have a lot of current flowing through this. So you have this electromigration process is where flux of electrons flowing through this material pushes the atoms. Yeah, so they would actually, so this is, then the atoms will start to migrate. Okay, so that's called electromigration, and at some point of time you would actually have discontinuity in the film. Okay, an initial increase in the series resistance, and at some point it becomes open circuit. Okay. Now electromigration will be more severe if my deposition is like this. Yeah, 1 billion transistors I need to contact, meaning connect together, and to be sure that it's going to be like this everywhere. Okay, not like this. Very important consideration. Now, how do we define the step coverage? So the step coverage is nothing but thickness on the side wall divided by the thickness on the top. Okay? Ratio of this thickness to this thickness, and you multiply with 100 to get this step coverage in percentage. Now in thermal CVD you can get nearly 100%. PCVD you may be able to control it, but typically less than 100%. PVD is less than 100%, and you can get 0 step coverage in processes like MBE and thermal evaporation. Okay, so we'll see why soon. Now, in this example, we have discussed that due to electromigration and series resistance and so on and so forth, if I am looking at metal, okay, I would like to have a step coverage of 100%. But can you think of any process where step coverage of 0% is required? So there are actually there are laboratory processes, or I would also say small volume production processes, where you target 0 step coverage. Okay. Of course, ALD, yeah, ALD has 100% step coverage. 0 step coverage. Okay. Process that where you are looking for 0 step coverage. So there is a process called lift-off, okay, which is used by many students here, in fact, for making devices, typically for metal patterning on wafers. So in this process, what you do is the following. So you have a substrate, okay, and you want to okay, I have a substrate. Okay, this is my substrate, right? You can see it here. Okay, so you have a substrate. I'm really sorry about this. Apparently institute don't have money to change the lamps. Okay, so we have given sufficient number of complaints. I think it will be addressed soon. So you have a substrate with this kind of thing, and you want to make a pattern, yeah, a deposition of metal, okay, only at certain places. Okay, but my difficulty with any of these thin film deposition processes, except in very few cases, is that when I do the deposition, it will get deposited everywhere on the substrate. Okay, so the usual technique is to deposit first and then etch out things from where you don't want them. Okay, so you need to then use some chemical reaction to get rid of this, or some physical sputtering, yeah, to get rid of materials. The other is, so but then let's say I want to deposit gold selectively. That's not possible using any of the thin film deposition techniques that we mentioned. So you deposit it everywhere. But now if I want to etch gold without etching anything else, that's going to be a big challenge. Okay, because you need to use aqua regia to etch gold. It will etch most of the others. So I have a problem. So now this process, the lift off process, is a clever way to actually circumvent this problem. You deposit gold but etch something else. Okay. So what you are going to do is to deposit something like this. Okay. So typically you deposit photoresist. So you deposit photoresist. So photoresist is actually a material that is sensitive to light. Okay. So we'll see this process later on. And you can pattern. So you deposit the photoresist on the entire wafer surface, and then you expose it to light using a mask, and then can etch away the photoresist from certain regions by using a solvent. Okay. So I get this pattern. This is photoresist, right? This is my substrate. And now I deposit gold. Okay. By a process which has 0 step coverage. Okay. So what does it mean if I deposit gold with a process that has 0 step coverage? So this is photoresist, right? Okay. 0 step coverage. What does it mean if I deposit gold on top? Okay. So I would have gold deposited here at the bottom, not on the side walls. Yeah. So step coverage means thickness here divided by thickness on the top. 0 means there should be 0. Okay. Now the next step is to etch what? I don't want to etch the gold. Meaning, yeah, but that would be a meaning. We did not want to etch the gold. That was the starting point. I don't want to etch gold. Okay. So I etch the photoresist. Okay. I strip the photoresist. So again I can use some organic solvents to etch away this thing. Now if I etch the photoresist, what would remain? Okay. So this would be gone. Right? This would also be gone. Okay. So I'll end with wafer which has only this. Okay. So you would essentially etch. So if I am now etching the photoresist, right? So the photoresist will be etched. The solvent would attack the photoresist from the sides. Right? It is exposed here. Yeah. If there is metal here, then the photoresist will be protected from the solvent. Okay. So but because the step coverage is 0, it can be attacked from the sides. Okay. So I would actually get rid of this whole thing. Right. Please look there. Yeah. So I'll end with a gold pattern here. So this is called lift off process. Okay. So here you want so you are trying to actually make a line or pattern of a metal or a material that is very difficult to etch. Okay. So you don't etch it, you etch the photoresist. Now if you look at the properties of interest from an application point, right, for VLSI for example, electrical properties are important. So if you look at metals, you usually target high conductivity. Okay. And it should be robust against electromigration, which I already mentioned. And you may think that, okay, electromigration for copper, for example, this is going to be decided by the properties of the material. But we already discussed that it also depends on the step coverage, right, and the uniformity in thickness, and so on and so forth. But there are other factors. For example, if you take copper, yeah, or gold, whatever metal you use, you deposit it usually would be in the form of polycrystalline. It would be polycrystalline material. Now, bigger the grain size, okay. So in the polycrystalline material you have crystallites of different orientation, right. So the larger the grain size, more robust the material or the film to electromagnetic. Less number of voids and other impurities and so on can actually make it better. Semiconductors, so very important, controlled conductivity. So we want to control the doping level, right? Low density of generation recombination centers. So low density of stacking faults, twins, etc. for low junction leakage and high breakdown voltage. Controlled stress and strain in these films. And for dielectrics, of course, we need good insulating properties. So this would mean low leakage currents, high breakdown fields, low density of charge traps and pinholes. Dielectric constants should be sufficiently high. You may think that, okay, I have silicon dioxide dielectric constant is 3.9, but that is not true, depending on the deposition process, how dense the film is, and what are things there in the film, the dielectric constant can vary. Okay? And another very important consideration is the high quality of the interface between materials. Okay? So if I have silicon dioxide deposited on silicon, for example, for gate oxide applications, you would like to have extremely good quality interface. So I already mentioned, I think in a previous lecture we had discussed what is meant by a good quality interface. Interface state density should be low, right, and the charges in the oxide should be low. Okay, it's not necessarily the requirement for that particular application that these properties are low. Usually you want interface states to be low. Okay, but in photovoltaic applications you may actually would like to have some charges at the interface in some applications. Now all properties, so this is very, very important because you, as I mentioned, if you say, okay, this is the material, silicon, right, you can go to some reference books and so on which actually list out the properties of silicon. Okay, but the deposition conditions would decide lot of the values of this property. I mentioned already that high conductivity and robustness against electromigration for metals would depend on the grain size. Okay, so deposition conditions can be controlled to get appropriate grain size. For example, the grain size would depend on the process temperature. Yeah. Semiconductors, low density of generation recombination centers, influenced by the growth rate, temperature, presence of impurities in the precursor, and so on. Crystalline phase, so you can see amorphous. So if I deposit silicon, for example, okay, on silicon, depending on the process conditions, I can get amorphous silicon, nanocrystalline or microcrystalline silicon, or polycrystalline, which is larger grains, or monocrystalline, depending on the process temperature, and if you're using plasma processes, depending on the plasma power, and so on. Okay, so this is something that I would actually leave you to just go through, and here we will see the vacuum as high, ultra high, and so on, and we are talking about high vacuum in this range, yeah, 0.1 to 10 raised to minus 7 Pascal, ultra high vacuum in this range, so minus 10 raised to minus 7 to 10 raised to minus 10. Okay. So the importance of this we would see shortly. Now, okay, so one thing that I would actually mention, you can read these things yourself. Okay, if I look at MBE, for example, yeah, MBE, okay, the thickness uniformity is okay, sharp interface is good, smooth interface good, sharp dopant profile is good, step coverage is very poor, okay, almost zero, deposition rate, okay, fine, vacuum is ultra high, industrial applications vary, okay. So a lot of things are not good for this process, yeah, and when you say ultra high vacuum, what does it mean? So it's actually very difficult to run an ultra high vacuum system in a place like IIT Bombay, okay. Forget about many other places in the country. And the reason is very simple. See, we have these 2-3 MBE systems, yeah. Suppose you got the system to high vacuum condition, and then the power goes off. Gone. Okay. Now to get you the vacuum back, how many days you think? How many hours? 6, 7 hours. She says 6, 7 hours. Few months, 3 months. No, that does not. See, what happens is that, actually when you are talking about this kind of vacuum conditions, right, every molecule that comes out of the surface of the chamber, okay, so this is not trivial, yeah. So if you operate, if anybody goes and do thermal evaporation, electron beam evaporation kind of processes, for a moment take your eyes off your mobile phone and look at the vacuum gauge, okay, when it goes to fairly high vacuum conditions, right, somewhere 10 raised to -5 and so on and so forth. So it goes, the needle goes, right, the vacuum, if it has a needle, or even digital gauges, you should be able to see this. So high vacuum, okay, and suddenly it comes back for a short duration and goes back, okay. So what was this fluctuation? You think that it's a noise? No, but why did it come back to a high pressure condition and then starts going back again, but a fairly fast rise in the vacuum. See, these are some gas that is trapped on the walls of the chamber, okay. Suppose you were depositing aluminum, right, and some aluminum is there, and when you opened it, it flaked off a little bit. So some air got trapped inside, yeah. Now, I close this chamber, I am evacuating, okay. At some point, this air will come out, okay. That's because there is a huge pressure difference between the air bubble that is there and the chamber. So it comes out. So it takes so many months to get all these things out if I am going to this kind of level. Okay. So this is, now you need to have very good quality power. Bombay, you don't feel much of power cut, right? But even 10 minutes you have a big problem. So we have, for example, recently got a diesel generator. So colleagues who are working on this fought a lot for this, and now they have something like this. So industrial process, now it's so difficult to manage such a thing unless you have very good quality power and so on and so forth. So you may think that industrial applications, this is a no-brainer, the better I don't have it, right, for anything. But there are certain applications where you can't do with anything else. Okay. So these are very high quality detectors, cameras and so on. These are that are used in satellites and military applications. Okay. You may actually not be able to use any other technique to get the same level of sensitivity. Okay. So if you look at the basic thin film process, we'll end with this. So we have a source, right? And then you transport the material from the source, and on the way it may react, okay, and then you have a deposition with maybe a reaction on the surface that forms the film. And then when you do this, so this can be a solid, liquid or vapor or gas, and the transport medium can be vacuum, plasma or a liquid, and substrate conditions are important for deposition, so you need to control this. Then you get the film, and you need to do at every stage, especially in research, actually do measurements of all these things. Yeah. So it is possible to observe a lot of things in situ as the deposition is going on. Okay. Then if you look at some of this R&D MBE reactors, you would have a lot of things to really see what is going on inside and characterize the films as they are being deposited. Okay. Okay, so we'll continue the discussion in the next class. Yeah.